The challenge? Measure the massive flow of water coursing northward through the Samoan Passage, 3 miles deep in the South Pacific. Wave chasers Matthew Alford and John Nickett from the Applied Physics Laboratory at the University of Washington got their first on-site look at the Samoan Passage in the fall of 2011.
Last night we deployed our instrument package, beginning to do our time series inside the Samoan Passage. Very exciting.
In the water.
Roger, in the water, thank you.
You think about the ocean circulation as kind of a big waterworks. And there's lots of big pipes and little pipes. And the Samoan Passage is a very, very narrow pipe. And all of the water that has sunk from the surface in Antarctica all the way to the bottom and has traveled all this way through the South Pacific has now got to squeeze its way through the Samoan Passage on its way into the North Pacific.
We're hoping to get better estimates of flow. Right, there have been some long-term current measurements here a couple decades ago. We are hoping to put a more extensive array of instruments out so we can get a better idea of the volume of this deep, cold bottom water that's moving north through the gaps.
It's a really pretty exciting area because it's a lot of water. We're talking about 6,000 tons of water every second flowing through this narrow gap, which is about 35 Amazon rivers. So you can really think about just how much that water is really representing down there. And it's 3 miles beneath the sea surface, flowing beneath us as part of that global conveyor belt.
That conveyor belt, the global thermohaline circulation system, affects global climate. Alford and Nickett believe the Samoan Passage will yield new insights into climate change.
We're zooming in on a little specific piece of this overturning circulation, one that we think we can resolve, and that also has a history here so we can understand how it's changing in time.
The fall 2011 cruise allowed testing of an improved ADCP-CTD instrument system.
But usually those ADCPs have to record their data internally. And so what we've done is developed a system by which the ADCPs transmit their data up the wire, and they also get power from a battery system down on the package. Okay. So that's a substantial improvement because it really lets us look at the data in real time, which both lets us make sure the instruments are working, and it also lets us monitor the data and make quicker decisions based on what we're finding.
Another goal, achieve more accurate multi-beam mapping of the Samoan Passage, key to determining precise pathways of the flow. This time out, a surprise. Water 3 miles deep moving unexpectedly fast.
There's incredibly accelerated flows. And so you would move from a 0 meters per second flow down into perhaps 30 centimeters per second or even 50 centimeters a second, maybe even more, we don't know yet. By abyssal ocean standards, it's really a wampum flow.
The ultimate goal is to weave all of this new and better data into improved computer models of the complex natural forces at work. These new models, in turn, will provide a clearer view into the future of the Earth's oceans and the global climate.
Science at work for you. This is APL, the Applied Physics Laboratory at the University of Washington in Seattle.